Hi everyone, my name is Indira Lakita with the student ID number ending in 080. Today we're going to move on to Chapter 10, Chapter 11, which is about metal casting, processes, and equipment. This chapter introduces metal casting as one of the oldest and most versatile manufacturing processes. In casting, molten metal is poured into a mold to form a desired shape after solidification. Its importance is in producing components with complex geometries that would be difficult or costly to machine, with emphasis that casting supports both small-scale and mass production from jewelry to engine blocks, and how modern casting integrates automation, precise control, and advanced materials to achieve better quality and efficiency. Here I have made a table of the classifications of the casting processes. Casting processes are classified based on mold and pattern reusability. So for the mold expandable, its pattern is permanent, and an example of the processing is sand casting. Another example of expandable, which the pattern is also expandable, an example of that is investment casting. And for the mold permanent, which the pattern will also be permanent, an example of the process that uses that is die casting. Table 11.1 shows the summary of casting processes. Moving on to figure 11.1, with A being a typical gray iron casting used in automobiles, including the transmission valve body on the left and the hub rotor with disc brake cylinder to the front. And moving on to the B, it is a cast transmission housing with C, the polarization of PDC 2000 digital camera with an AC191D die cast, high purity in magnesium case. Moving on to D, it is a two-piece Polaroid camera case made by the hot chamber die casting processes. Here we have another table of 11.2, which is the general characteristics of the casting processes. So there is material cast, and there is also the waste, the typical surface, the prosperity, shape, complexity, and all of that. In this category, the mold is destroyed after each casting, but the pattern is reused. Common examples include sand casting and plaster mold casting. The flexibility of using expandable molds for complex shapes and large parts stress that these processes are cost-effective for low to medium production volumes. The key steps include pattern, preparation, mold making, melting, pouring, and shake out. Point out that sand and plaster molds allow gases to escape easily, reducing effects like porosity. Moving on to 11.2.1, which is sand casting. Sand casting is the most widely used metal casting method. The sand acts as the mold material held together by clay or chemical binder. The mold is made around a pattern, then removed and filled with molten metal. After solidification, the mold is broken to release the casting. It's suitable for nearly all metals and large parts such as engine blocks or pump housing. The surface finish and accuracy depend on the sand quality and also mold compaction. Here in this slide, we discuss the materials for sand casting. Most commonly are silica, zircon, perlite, or olivine, and binders that are used such as clay, organic resins, sodium silicate, and so on. The advantages of sand casting is it's simple and versatile, it's suitable for ferrous or non-ferrous metals, and can produce very large or very small parts. Although it has limitations including poor dimensional accuracy, rough surface finish, and slower production rate. Below here is the outline of production steps in typical sand casting operation. Shell molding is a precision casting process that uses a thin resin-coated sand shell formed on a heated metal pattern. The process begins by heating the metal pattern, applying the resin-coated sand, and allowing a thin layer to harden into a strong mold shell. The shell halves are baked, assembled, and filled with molten metal. After solidification, the shell is broken to remove the casting. This method gives excellent surface finish, high dimensional accuracy, and requires less sand than conventional sand casting. It's ideal for small to medium casting and well suited for mass production. Common examples include gear housing, connecting rods, and valve bodies made from both ferrous and non-ferrous metals. Although the tooling cost is higher, the process is efficient, clean, and capable of producing consistent, high-quality parts for automotive and industrial applications. This is an illustration of the sand molding, and it shows various features from the drag, cope, open riser, pouring basin, the vent, the blind riser, the mold cavity, the well runner gate, sand, flask, spear, more sand, choke, and the parting line. Now this is the taper on patterns for ease of removal from the sand mold. Now this is an example of the sand course showing core prints and caplets to support the course. This is the vertical flaskless molding, with A being sand and squeezed between two halves of the pattern, and the image in the middle, B, assembled molds passing along an assembly line for pouring, and the one on the very right is a photography of a vertical flakless molding line, with the source from American Foundry Society. Shell molding is a casting process that uses a thin shell of resin-coated sand to create the mold. The process starts with a heated metal pattern that's coated with the resin sand mixture. The heat cures a thin layer, forming a hard shell mold about 5 to 10 millimeters thick. The shell's halves are removed, baked for strength, and clamped together for pouring. This method produces excellent surface finish and dimensional accuracy while using less and compared to conventional sand casting. It's efficient for small to medium parts. It is ideal for mass production. Typical applications include gear housing, valve bodies, camshaft, and brackets. Although pattern cost is higher, the quality and repeatability make it worthwhile for precision manufacturing. Now this is the schematic illustrations of the sequence of operations for sand casting, with A being a mechanical drawing of the part is used to generate a drawing for the pattern. Considerations such as part shrinkage and draft must be built into the drawing already, and patterns that have been mounted on plates equipped with pins for alignment. Note that the presence of core prints designed to be hold in the core in place. And the core boxes produces core hops, which are pasted together later on. The cores will be used to produce the hollow area for the part shown in the drawing A, or on the very left. This is the continuation of the drawing, or of the parts. The core boxes produce core hops, which are pasted together. The cores will be used to produce the hollow area that we have shown in part A. Moving on to F, the cope half of the mold is assembled by securing the cope pattern plate to flask with aligning pins and attaching inserts from the screws and risers. Now once all of that is completed, the core is set in place with the drag cavity, and the mold is closed by placing the cope on top of the drag and securing the assembly with pins. The flasks are then subjected to pressure to counteract buoyant forces in the liquid, which might lift the cope. After the metal solidifies, the casting is removed from the mold. The spear and risers are cut off and recycled, and the casting is then cleaned, inspected, and heat treated if it is necessary. This is the shell molding process, or also called the dump box technique. Plaster mold casting uses a mixture of gypsum plaster, water, and additives to create a smooth, precise mold. The process begins by pouring the plaster slurry over a pattern. Once the plaster sets, the pattern is removed and the mold is dried and baked to remove moisture. Molten metal is then poured into the mold cavity. This process provides excellent surface finish and dimensional accuracy, similar to investment casting, but at a much lower cost. It's suitable for non-ferrous metal like aluminum, magnesium, and copper alloys. However, because plaster cannot withstand very high temperature, it's not used for ferrous metals. Typical applications for this include fine details and smooth surface, such as aircraft parts, pump housing, and decorative items. The main limitation is that drying time and mold handling make it slower than other expandable mold processes. And this is the applications and advantages. The advantages include excellent surface finish and close dimensional accuracy. It can reproduce fine details in thin walls, and it is a low-cost tooling for small batches. Ceramic mold casting is similar to plaster mold casting but uses a refractory ceramic material instead of a plaster. The mold is made by pouring a slurry of fine ceramic particles, binder, and water over a pattern. Once hardened, the mold is removed, dried, and fired at a high temperature to increase its strength and heat resistance. This process allows casting of both ferrous and non-ferrous metals, including steels and superalloys. Due to the high temperature capability of ceramic materials, it produces excellent surface finish and dimensional accuracy, making it ideal for intricate shapes and parts requiring high strength. Common applications include turbine blades, valves, and precision engineering components. Although the molds are expandable and more expensive than sand or plaster mold, they offer superior performance and quality for high temperature alloys and critical parts. This is a sequence of operations in making ceramic mold. Expandable mold, expandable pattern casting processes are those in which both the mold and the pattern are destroyed after each casting. These methods are used when producing parts with complex shapes that would be difficult to make with reusable molds. The two main processes in this category are evaporative pattern casting, or lost foam, and investment casting, or low wax. In low foam casting, the foam pattern evaporates as molten metal is poured in, while in investment casting, a wax pattern is melted out of a ceramic shell before pouring. Both methods offer excellent dimensional accuracy and surface quality. Lost foam is preferred for larger castings like engine blocks, whereas investment casting is used for smaller, intricate components such as turbine blades or jewelry. Though more expensive, these processes eliminate parting lines, reduce machining, and are ideal when precision and detail are critical. Here I have made a table for a simple comparison overview of the process, the mold material accuracy, cost, and also what metals are suitable for each of them. Evaporative pattern casting, also known as the lost foam process, uses a pattern made of polystyrene foam that evaporates when molten metal is poured into the mold. The foam pattern is coated with a refractory material to reduce its surface and then placed in a flask filled with unbonded sand. When molten metal is poured, the foam pattern evaporates and the metal replaces it exactly, forming the casting. This process eliminates the need for parting lines, cores, and metal removal, making it ideal for complex shapes. It produces good dimensional accuracy and surface finish while reducing machining and waste. However, because the foam pattern is destroyed each time, it's used mainly for medium to large castings, such as engine blocks and manifolds, where precision and cost efficiency are most important. And these are the advantages and limitations that I have talked about just before. Now this drawing is an example of an expandable pattern casting process, or the lost foam or evaporative pattern casting. Investment casting, also known as the lost wax process, uses a wax pattern that is coated with a ceramic slurry to form a strong shell mold. After the shell hardens, the wax is melted out, leaving a cavity in the shape of the final part. The mold is then heated and molten metal is poured into to fill the cavity. This process produces parts with exceptional accuracy, fine detail, and smooth surface, making it ideal for complex or intricate geometries. It requires little to no machining after casting. Although investment casting is more costly and time-consuming, it is widely used in aerospace, jewelry, and medical industries for producing high-precision components such as turbine blades, gears, and implants, where surface quality and tight tolerances are essential. Now, this illustration is an example of the investment casting, or the lost wax process casting. Produced by this method can be made with very fine detail and from a variety of metals. Moving on, this is investment casting of an integrally cast rotor for a gas turbine with A. the wax pattern assembly, B. ceramic shell around the wax pattern, C. wax is melted out and the mold is filled under a vacuum while molten superalloy, and D. the cast rotor produced to net or near net shape. Permanent mold casting processes use reusable metal molds instead of expandable sand or ceramic molds. These molds are typically made of cast iron, steel, or graphite and are coated with refractory materials to prevent sticking and extend mold life. Molten metal is poured or forced into the metal mold where it cools and solidifies rapidly. This rapid cooling produces a fine-grained, dense structure with good surface finish and high dimensional accuracy. Permanent mold casting is ideal for non-ferrous metals such as aluminium, magnesium, and copper alloys. It's commonly used for medium to high volume production of parts like piston, wheels, and gear housing. The main advantages are consistent quality and good mechanical properties, while the limitations include high mold costs and design restrictions for complex shapes. This is a schematic illustration of the vacuum casting process. The mold has a bottom gate, with the A being the before and the B is the after immersion of the mold into the molten metal. Vacuum casting is a version of pressure casting that uses a vacuum to draw molten metal into the mold cavity rather than pushing it with a gas pressure. By removing air and gases from the mold, this process minimizes turbulence during filling and eliminates gas porosity. The molten metal is poured into a vacuum-sealed chamber where the reduced pressure pulls the metal smoothly into the mold. This results in a dense, clean, and high-quality casting with superior surface finish and dimensional accuracy. Vacuum casting is especially useful for reactive and high-performance alloys such as titanium, aluminum, and superalloys, which can easily oxidize when exposed to air. It is commonly used in aerospace and precision engineering, where material integrity and fine detail are critical. Although equipment costs are high, vacuum casting offers excellent mechanical properties, minimal defects, and improved reproducibility, making it ideal for demand applications. Slash casting is a special type of permanent mold casting used to produce thin-walled, hollow parts without the use of cores. The process begins by pouring molten metal into a preheated metal mold. After a short period, a thin shell of metal solidifies along the mold surface. The mold is then inverted, and the unsolidified molten metal is drained out, leaving behind a hollow shell. The result is a lightweight casting with smooth surface and detailed features. This method is typically used with low melting point metals such as zinc, tin, and lead alloys. It's ideal for decorative and ornamental products such as lamp bases, figurines, toys, and prototype parts. While sludge casting offers simplicity and excellent surface finish, the wall thickness is difficult to control and the parts produced are not suitable for structural or load-bearing applications. Pressure casting is a permanent mold process where molten metal is forced into the mold cavity using gas pressure instead of gravity. The pressure is maintained during solidification to ensure a dense, porosity-free structure. In this process, the mold is placed above a sealed crucible filled with molten metal. When gas pressure, typically between 70 to 700 kilopascals, is applied, the metal is pushed upward through a riser tube into the mold cavity. Once the metal solidifies, the pressure is released and any remaining liquid metal flows back into the crucible. Pressure casting produces casting with excellent mechanical strength, surface quality, and dimensional accuracy, while minimizing oxidation and metal waste. It is commonly used for aluminium, magnesium, and copper alloys in the production of automotive and aerospace components, such as wheels and cylinder heads. Although the equipment is more complex and costly, pressure casting offers high efficiency and consistent quality, making it suitable for precision, high-performance applications. Moving on to 11.4.5, die casting. Die casting is a high-speed, high-pressure process in which molten metal is injected into a hardened steel mold called a die, where it solidifies under pressure. The die is reusable and designed for fast production of precise, detailed parts. There are two main types: a hot chamber die casting, where the molten metal is melted into an attached chamber and injected directly into the die. It's used for low melting point alloys like zinc, lead, and magnesium. And the second one is cold chamber die casting, where molten metal is ladled into the chamber for each shot. It's used for higher melting metals like aluminum and or copper alloys. This process offers excellent surface finish, tight tolerance, and thin walls, making it ideal for mass production of components such as automotive housings, power tools, and appliance parts. However, the initial die and equipment costs are high, and the process can produce porosity if air becomes trapped during injection. Despite these limitations, die casting remains one of the most efficient and widely used casting methods for large volume precision manufacturing. Now, this is a schematic illustration of a hot chamber die casting process. Here on the very left, we can see the injector die and the die cavity and the cover die, and then on the right is the hydraulic shot cylinder, making it the plunger rock and gooseneck that is pouring the molten metal into the pot, and below is the furnace. Figure 11.20 is also a schematic illustration of the cold chamber die casting process. These machines are larger compared to the size of the casting because high forces are required to keep the two halves of the dies closed under pressure. Now here we have table 11.3, which is the properties and typical applications of some common die casting alloys. This is also an example of the different types of the cavities in die casting die. There is a single cavity die, there is multiple cavity die, combination die, and on the very right is the unit die. Centrifugal casting is a process in which molten metal is poured into a rotating mold, and the centrifugal force distributes the metal against the mold walls. The rapid spinning ensures that denser metal moves outward while impurities and gases moves toward the inner surface. There are three main types. There is true centrifugal casting, which produces a hollow cylindrical parts like pipes, bushing, and bearings without using cores. The second is semi-centrifugal casting. It is used for solid parts such as wheels and pulleys in improving density at the outer rim. And the very last one, third, centrifuging. It involves multiple small molds arranged on a rotating arm to cast small, detailed parts like jewelry. This process creates dense, fine-grained, and defect-free casting with excellent mechanical properties. It's ideal for symmetrical parts that require high strength and durability. Although limited to axisymmetrical shapes, centrifugal casting offers superior metallurgical quality and is widely used in automotive, aerospace, and energy industries for producing components that must withstand high stress and wear. Now this is an illustration of the centrifugal casting process, with 5 cylinder liners and with A being a schematic illustrations of the centrifugal casting process, with pipes, cylindrical liners, and similarly shaped parts can be cast with this process. On the right is a side view of the machine. So we can see the drive roller. The mold is in between the drive roller and the free roller. This is also an illustration of the semi-centrifugal casting. Wheels with spokes can be cast by this process, and on the B is an illustration of casting by centrifuging. The molds are placed at the periphery of the machine, and the molten metal is forced into the molds by centrifugal force. Now moving on to squeeze casting and semi-solid metal forming. Squeeze casting is a hybrid process that combines features of casting and forging to produce dense, high-strength parts. In this process, molten metal is poured into a preheated die, and a hydraulic punch applies pressure, typically up to 150 megapascals, during solidification. The applied pressure eliminates gas porosity and shrinkage, resulting in a fine-grained, defect-free structure with excellent mechanical properties. Because the metal solidifies under pressure, heat transfer is faster, improving surface finish and dimensional accuracy. Squeeze casting is commonly used for aluminum and magnesium alloys to manufacture automotive and aerospace components such as piston, wheels, and structural parts. It allows the use of heat-treatable alloys, reduces machining needs, and enhances fatigue strength. Although equipment and tooling costs are higher, the process offers exceptional quality and is ideal for near-net shape production where strength, precision, and reliability are essential. Now here, this illustrates the sequence of operations in the squeeze casting process. This process combines the advantages of casting and forging. So the first is the metal, second is the pour molten metal into the die, then we close the die and apply pressure, and then lastly we eject squeeze casting, charge metal stock, and then we repeat the cycle. And SSM forming or semi-solid metal forming is a process where metal is partially solid, 30% to 60% solid, before shaping, allowing thixotropic flow under pressure. The techniques used is the thixocasting, using a precast billet reheated to the semi-solid state, and rear-casting form semi-solid slurry directed form molten metal. The advantages is the smooth laminar flow, reducing defects and porosity. Other advantages from the SSM forming is the lower filling force and extended die lifetime. It is capable of forming complex thin walled shapes and its excellent dimensional accuracy and repeatability. Although it has limitations include complex equipment and precise temperature control is required, and is also limited to specific alloys with a wide freezing range. The applications for this is automotive, such as brake components, electric housing, and aerospace parts. Composite mold casting uses two or more different materials to make a single mold, combining the advantages of each material for better performance and cost efficiency. These materials can include metal, sand, graphite, or ceramic, depending on the requirement of the casting. For example, metal inserts, called chills, can be placed in a sand mold to accelerate cooling in specific regions, refining the grain structure and improving strength locally. Similarly, ceramic or graphite layers can be added to improve heat resistance or prevent chemical reaction between the molten metal and the mold. This process provides better thermal control, improved surface finish, and dimensional accuracy while reducing overall material cost. It's especially useful for large or complex parts where different sections of the mold require different cooling or strength characteristics. Composite molds are commonly used for turbine housing, large cast iron parts, and tool or die components. Although mold preparation is more complex, the resulting casting exhibits superior quality and performance compared to conventional sand molds. Casting techniques for single crystal components are designed to produce parts made of one continuous crystal structure with no grain boundaries. Eliminating grain boundaries significantly improves high temperature strength, fatigue resistance, and creep performance, which is critical for components exposed to extreme heat and stress. The process begins with directional solidification, where a molten alloy solidifies from one end under a controlled temperature gradient. A seed crystal at the base defines the desired crystal orientation, and only that orientation continues to grow as the mold is slowly withdrawn from this furnace. One common method is the Bridgman process, which carefully controls the withdrawal rate and temperature to ensure single crystal growth. Single crystal casting is primarily used for jet engine turbine blades, gas turbine components, and other high-performance applications where conventional casting would fail under prolonged thermal and mechanical loads. Although the process is complex and expensive, it delivers unmatched performance, making it essential for aerospace and energy industries that demand material capable of withstanding extreme operating conditions. This is a method of casting turbine blades, with A is the directional solidification, B, method to produce a single crystal blade, and C, on the very right, is a single crystal blade with the construction portion still attached. Now this is the two methods of crystal growing, with the A being crystal pulling, or the Czochralski process. The one in the middle is the floating zone method, which crystal growing is especially important in the semiconductor industry, and the one on the very right is a single crystal ingot produced by the Czochralski process. Rapid solidification is a process in which molten metal is cooled at extremely high rates, typically between 10 by the power of 4 and 10 by the power of 6 degrees Celsius per second, to create unique microstructure not achievable by conventional cooling. This ultra-fast cooling refines the grain size, reduces microsegregation, and can even produce amorphous or glassy metals where atoms are frozen in a disordered state. The result is a material with high strength, improved toughness, and enhanced corrosion resistance. Common rapid solidification method include melt spinning, where molten metal is sprayed onto a rapidly rotating chill wheel to form thin ribbons. And second one is a spot cooling, which rapidly quenches small droplets on a cold substrate. And the last one is atomization, where molten metal is broken into fine droplets by gas or water, forming powders used in powder metallurgy and 3D printing. These techniques are widely used to produce high-performance alloys, magnetic materials, and aerospace components. Rapid solidification allows the development of new alloy composition and microstructure, giving engineers better control over material properties and performance. This one on the left is a schematic illustration of melt spinning to produce thin strips of amorphous metal, and the one on the right is a photograph of nickel alloy production through melt spinning. Moving on to 11.7, inspection of casting. Inspection of casting is carried out to ensure that every product meets the required dimensional accuracy, service quality, and internal integrity. It helps identify defects early, improving both safety and reliability of the final component. It begins with visual inspection, the simplest method used to detect surface defects like cracks, misruns, cold struts, or surface toughness. Then explain dimensional inspection, which uses tools such as calipers, micrometers, or coordinate measuring machines, or CMM, to verify size and tolerance. Next, cover constructive testing or NDT methods, including radiographic testing, such as X-ray or gamma ray. It detects internal voids, porosity, or shrinkage defects. Next is ultrasonic testing. It identifies internal discontinuities using sound waves. Magnetic particle testing, used on ferromagnetic metals to reveal surface and near-surface cracks. And lastly, dye penetrate testing for non-ferrous metals, highlight surface cracks and porosity. Finally, destructive tests, tensile hardness and impact tests, used on sample casting to confirm mechanical properties. Stress that thorough inspection ensures casting meet design standards and provides feedback to improve mold design, melting practice, and overall process control. Now, there are two types of melting furnaces used in foundries. The A on the left is a crucible, and the one on the right is a coupler. Melting practice involves all the steps needed to produce clean, homogeneous, and properly alloyed metal molten before casting. It plays a crucial role in determining the quality, mechanical properties, and consistency of the final casting. The main objectives are to achieve the correct chemical composition, maintain optimal temperature for fluidity, and remove impurities, inclusions, and dissolved gases. Fluxes are added to trap oxide and slag, while the casting agents eliminate gases like hydrogen that can cause porosity. Moving on, we're going to go into the types of furnace. The first being crucible furnace. It is a small-scale fuel or electric heated, ideal for non-ferrous metal. There is coupler furnace, a continuous coke-fired furnace used mainly for melting cast iron. There is induction furnace, used for electromagnetic induction for precise, clean, and efficient melting, suitable for both ferrous and non-ferrous alloys. Then there is electric arc furnace. It generates high temperature with electric arcs, used for steel and high alloy metals. Gold melting practices ensures consistent alloy chemistry, minimize oxidation, and reduce defects. It emphasizes that temperature control and cleanliness are vital for achieving sound, high-quality casting ready for pouring. Now lastly, 11.9, foundries and foundry automation. Foundries are specialized facilities while all melting, casting operations take place, from pattern and mold making to melting, pouring, killing, and finishing. Modern foundries combine traditional casting techniques with advanced automation and digital technologies to improve quality, productivity, and safety. There are 5 main stages of a foundry operation. The first being pattern and core making. It is creating molds and cores based on design specification. Second, molding and melting. It prepares molds and melting metals in furnace. The third being molding and melting, the third being pouring and solidification, carefully filling molds and allowing the metal to solidify. The fourth, shake out, cleaning and finishing, removing sand, flash, and surface defects. 5, inspection and testing, ensuring dimensional accuracy and material integrity. Lastly, inspection and testing, it ensures casting meets quality and dimensional standards. There are foundry automation, which includes CAD and CAM systems for precise pattern and mold designs, robotics for pouring, handling, and cleaning castings, sensors and monitoring system for temperature and process controls, automated inspection systems for real-time defect detection, and Industry 4.0 integration linking all equipment for data-driven process optimization. Automation in foundries lead to higher efficiency, consistent produced quality, improved worker safety, and reduced material waste. Modern foundry is evolving into a smart, interconnected manufacturing environment that combines craftsmanship with advanced technology. That is all that I have to offer for Chapter 11. I deeply apologize if I misinformed anything, and thank you so much for watching, and I'll see you next time. Bye!